Hey guys, welcome back to AP Pre-Calc. This is lesson 1.5. Let's get right into it. All right, so here's the bell ringer for today. Pause the video if you haven't done so already, because I am about to go over the answer. So here we have a polynomial function j. We want to know how many points of inflection there is. And so here there is going to be a point of inflection in between any peak or valley. So you want to find all the peaks and valleys, which I have there, and then around, not always, but around halfway in between, you will typically find a point of inflection. It's only in between peaks and valleys, so not on the outside. So this should only have 2 points of inflection. Notice by definition, this is where the graph changes concavity, so where it goes from concave up to concave down, and then maybe back to concave up. The points of inflection, you don't need to know where they're located, you just need to know how to find how many there are on a graph. All right, so today we're going to be talking about the zeros of a polynomial. So let's say we have a polynomial function, let's go p of x, that looks like, let's go x minus 3 and then x plus 4. We want to find values that we can plug in for x that would make this equation equal to 0. And so we should have x equals 3 and x equals negative 4 as our two values. These are going to be called our zeros. They could be called our roots, our solutions, or even our x-intercepts. So all of these are names for the zero of an equation. And it makes sense, right? You plug it in, you get 0 as an output. And so that's why they're called that. But likewise, one other thing that you may not have known is if we have the zeros, we can write at least what we know to be linear factors of this polynomial, which is x minus the 0, so minus 3, and then this should be x minus negative 4, so x plus 4. That will always be the true for any polynomial function. Of course, there could be maybe a constant out here that is a scaling factor, but we know at least the polynomial will be divisible by x minus 3 and x plus 4. All right, so today we're also going to talk on the multiplicity of a factor. So let's take a look at those two linear factors that we just looked at, x minus 3, x plus 4. There we go. And now let's raise it to some different exponents. Maybe we do x minus 3 squared and x plus 4 cubed, right? The 0 at x equals 3 is going to have what we call a multiplicity of 2. And the reason why it's 2 is because this is essentially going to be repeated 2 times, right? We have x minus 3, and then you have x plus 4, x plus 4, x plus 4. This is repeated 2 times, so that is what our multiplicity is. Likewise, if we have the 0, x equals negative 4 here, this is going to have a multiplicity of 3, and that's going to be whatever that exponent is there. All right, so typically when we look at zeros, like if we just take a quadratic function like that, we know that it typically passes through the 0. If we graph this function at 3 and negative 4, that's what this quadratic would look like, and it just goes straight through both of those zeros. But sometimes there's a case where it may go straight through, or it may bounce off, the graph may bounce off at a 0. It's still a 0 at that point, but this is indicative of an even multiplicity. So when the multiplicity is even, the polynomial function will bounce off that graph. When the multiplicity is odd, the polynomial function will go straight through. So this is going to be an example of an odd multiplicity. So that's one thing that we will kind of talk about later as well and explore in a little bit more detail. So first, try example 1. Here we want to find all real zeros, state the multiplicity for each one, and then determine the degree. So if we walk through example A, to find all the zeros, we have 1 at x equals 0. And this is pretty important, right? If we don't write x plus 0 as a 0 because that's redundant. So we always just leave that as x. So this is x plus 0. We have one at x equals -1 and x equals +4. Here, the multiplicity of each one, the one of 0 is, this is like x plus 0 to the third power. So that's going to be our multiplicity. This should be 1. And then x minus 4 is squared. So 2 is going to be our multiplicity there. And now the final thing we need to do for part A is determine the degree. And so the degree is pretty simply all the multiplicities added up. So 3 plus 1 plus 2 is going to be 6, is going to be our degree for that polynomial. Taking a look at B, we see a difference of 2 squares. I'm probably going to want to factor that. So we have x plus 2, x minus 2, and then we have x minus 2 to the fourth. We could almost rewrite this by combining these two into a single x minus 2. And because there's 1 there and 4 on the right side, this is going to be x minus 2 to the fifth. So our zeros should be x equals -2 with a multiplicity of 1 and x equals +2 with a multiplicity of 5. And that should be our zeros there. And then our degree should be 6 as well. So just be cautious of that. Taking a look at our final one, we have x cubed minus x squared minus 6x. Let's factor that first. So here we can factor this into, take out an x and get x squared minus x minus 6. And then if we factor this trinomial, we get x minus 4, x minus 3. And now let's factor that other trinomial to get x times x minus 3, x plus 2, and then we still have x minus 4, x minus 3. So here our zeros should be at x equals 0 with a multiplicity of 1, x equals 3, and there's 2 of them, right? 1, 2, with a multiplicity of 2, x equals -2 with a multiplicity of 1, and then x equals +4 with a multiplicity of 1. So those would be all of our zeros there. And then our degree for that one is going to be 1 plus 2 plus 1 plus 1. So that should be 5. So our degree is 5 for part C. All right, so be prepared to do this on a test. I'll give you a polynomial and then ask you to find all the zeros and state the multiplicity of each zero. All right, so why does multiplicity behave in this way? And so first, just a quick refresher, what is -3 squared? That should be 9. And -3 cubed should be 27. Sorry, -27. Whoops. Oh, that was a close one there. So -27. And what can we say about how odd or even exponents affect negative numbers? Remember, if you have a negative number and you raise it to an odd exponent, you're going to get a negative number as an output. Or if you have a negative number, but this time you raise it to an even exponent, all those negatives should cancel out with each other, where you now get a positive number. And so that's what we really want to explore here when we look at the most basic example of an odd and even multiplicity for a zero. So let's take a look at the zero, x equals 0, right? So x equals 0, which is x, right, plus 0, which is the same thing as just x. And now let's take this 0 and raise it to the lowest odd and the lowest even number. So if we want a really basic example, x to the first and y equals x squared. And so this is going to be our odd example here, and then this is going to be our even example. And graphing both lines, that's what both graphs should look at. And so remember what we talked about negative numbers, that's going to come into play here. And so when we take a look at an odd multiplicity, if you have negative values as your x values, right, you take that and you raise it to an odd power. Of course, those positive values are going to be positive as well. But if we have negative numbers and you raise a negative number to an odd power, you're going to get negative numbers in return. So you're going to have points that are in this quadrant, and then they're going to turn positive when you take it to an odd power. when you take positive numbers to an odd power, right, they stay positive, but negative numbers are going to stay negative. And so it's going to go from negative to positive and cross through at the point x equals 0. Likewise, for y equals x squared, if you have positive numbers, those will of course stay positive. But if you have negative numbers, those will now turn positive because when you have something to an even power, all the negatives cancel out and you're going to be stuck on the same side of that positive. And so what you're seeing here is you're no longer going from negative to positive, you're going from positive to positive, in which case you are just directly bouncing off that graph at the point x equals 0. So that's kind of why the multiplicities behave this way. Of course, you won't ever have to like sketch these graphs or show this, but you will need to know that if it is an even multiplicity, it will bounce off the x-axis at that 0. All right, so here there are imaginary roots on the next slide. See if you can find them. So there they are, nice and clear, because they are not visible. So roots with an imaginary number, right? And so remember, imaginary numbers are ones that have an I term in there, are not visible, and that means you will not see them on the graph. So I think that should be the blank in your notes, is the word not. Let's take a look at this very simple function. So this is y equals x squared, but shifted up 1 unit. And so with this equation, we obviously know there's no zeros, right? There's no time where x is, where it crosses the x-intercept, or there's no time where it is a root or a solution to the graph, right? Because it is above the x-axis. So how can we find the zeros? And the answer is by doing it algebraically. Let's set this function equal to 0 and solve. So here, if you're trying to solve for x, I would subtract 1 from both sides to get -1 equals x squared, and then take the square root of both sides. Here you should just get x, and then this should be plus or minus, and remember the square root of -1 is, by definition, that imaginary number I. And because we're taking the square root, remember when you take the square root of a number, you want to have that plus or minus sign. That is going to be really important because, like we just saw, all imaginary roots come in pairs. What this means is if we have 3 plus 7i as a root, then we know 3 and then the opposite of that imaginary component, so 3 minus 7i, is also a root of the equation. These are called conjugate pairs or complex conjugate pairs, right? So you are only flipping the sign on the imaginary portion of the root. So to determine the conjugate of the following complex numbers, taking a look here, we have 4i. This will become -4i. Negative I, this becomes positive I. 2 minus 3i, this becomes 2 plus 3i. And then -4 plus 2i, this is -4 minus 2i. So that should be our answer there. So now what we're getting into is the fundamental theorem of algebra. And what this is a pretty cool sounding name, right? That sounds super important for a pretty lackluster theorem. And basically what it says is, like, let's say we have the zeros x equals 0, x equals 1, x equals 2, and x equals 3i, and then x equals -3i. And we have the multiplicities, multiplicity of 1, multiplicity of 2, multiplicity of 5, and then these all just have a multiplicity of 1. Basically, we can find the degree of this function by summing up all the multiplicities, which is 1 plus 2 plus 5 is 8, plus 1 plus 1 is 10. So this would be a degree of 10 by summing up all the multiplicities, but this time we include those complex zeros as well. And so we're going to use that to kind of help us with these next few questions. So let's see. These are good questions that I really like because they basically test everything that we've learned so far in this lesson. I will say the AP loves these questions too, so there's one on last year's AP exam. There will probably be one on your first test coming up, so just be prepared for that. All right, so for example 3, we have the graph of a polynomial function shown in the figure above. We know that x equals I root 3 is a 0. What is the least possible degree that we have with the information we are given? So we're given two parts of information, right? Verbally and graphically. We want to find as many zeros as we can, but not adding unnecessary zeros. And this is a hard question for a lot of students, so let's walk through this one together. What we're going to do here is look at the graph first, and let's find any zeros that we can identify on the graph. So I see one right there, and I see one at 3. So I'm going to put those zeros down at -1 and 3. Once we have our two zeros here, this is perfect. Now let's add their multiplicities in from what we can see on the graph. So at x equals 3, we'll start with that one. This goes straight through, so this has to be, all we know is that it could be an odd number, or it has to be an odd number, because it passes straight through. So it could be 1, 3, 5, 7, 9, who knows? But right now, all we know is it's an odd number, and we're looking for the lowest possible number, so we're just going to put 1 there. Now, at x equals -1, this is an example of when it bounces off at that 0, at -1. And so we know it has to have an even multiplicity, and so we want to put the lowest even number that we can. So in this case, we're going to put a multiplicity of 2. Now this is super, super important, right? What is stopping us from putting a multiplicity of like 6 or 12 or 207,000 for x equals -1, right? It is any even number. The reason for that is because we're trying to find the least possible value, so that's how we get a concrete answer. So those are our zeros that are shown on the graph. We are also given some information. Verbally, we're given x equals I times root 3 is a 0. We can assume that that's a multiplicity of 1, right? If it was repeated, they would say that. But if this is a 0, we also know that x equals -I root 3 should be a 0. Here, I think it's safe to assume that this also has a multiplicity of 1, and so this should be all of our zeros. We have our real zeros, and then we have our imaginary zeros, but we aren't even looking for all the zeros. We're looking for the degree of the polynomial, and this is the fundamental theorem of algebra, saying we can sum up all of these numbers to get our degree. So 2 plus 3 ones is 2 plus 3. This is 5. So 5 is our least possible value of n, which is just the degree. All right, so let's try these two. Pause the video now and work through these if you haven't yet, because I'm about to go over the answers. So here, if we write out all of our zeros, we have x equals 1. This has a multiplicity of 23. Wow. We also have x equals 3i. This is safe to assume a multiplicity of 1. With this comes along its best buddy, x equals -3i, which also has a multiplicity of 1. And then we have x equals 4 minus I and x equals 4 plus I. Those complex conjugates as well, each with a multiplicity of 1. So it should be 23 plus 4 ones, so we should get 27 as our least possible degree of that polynomial function there. That's a crazy polynomial looking at that. The next one we have, I'm not going to write out all these zeros, but we know that there's going to be 2 here from x equals 2 minus I and x equals 2 plus I. We know there's going to be 4. We're going to count 4 because of the multiplicity, and then 3 there for the same reason. And then here we have x equals -1 minus 5i. So this should be 2 that we're going to count as well. So 2 plus 4 plus 3 plus 2 should be 11, should be our answer there. All right, the final thing that we're going to talk about today is determining the degree of a polynomial given a table of values. And so the first thing we want to do when we're typically given a table of values is make sure it's over equally width or equal length input value intervals, right? That's kind of what we talked about in 1.3, and a lot of this is 1.3. We can determine the degree by examining the first difference, the second difference. You might now have to go into the third, fourth, fifth, or maybe even sixth difference. I know, it's crazy. The number of times you have to find that difference until it's the same number is the degree of the polynomial. I think the best way to show this is just by working through some examples. So example 6, determine the degree of the polynomial represented in the table below. So here, let's start by finding our first difference. With these problems, I just recommend being as meticulous as possible, making sure you're not making any simple algebra or just 8th grade or simple math errors, and really just stay organized and clean. These are not problems you can do in your head. All right, so here, -2 to -3, we're minusing 1. -3, -1 is +2. We have +5, and then +8. Continuing this, we have +3, +3, +3. So our first differences are not the same, but our second differences are. They're all +3. It's a beautiful looking table. And so our degree should be 2, because that's the numbered column that it takes for us to get the same number. Remember, any polynomial with a degree of 2 is also known as a quadratic function, which is really what we've learned in lesson 1.3 when determining if a function is linear or quadratic. But now we just may go that extra mile, that extra college try to find more polynomials such as cubic or even quartic polynomials. So let's take a look at B. Here, I'm going to look at the first difference for all of these. This should be -50, -50. This should be -48, -40. This should be -23, and then this should be +5. So we have our first difference. Obviously, it's not the same number, so we got to go one more. This is +0, +2, +8, +17, +28. So that looks good. Our second difference is not the same, so we're going to go a little bit further. So +2, +6, +9, +11. And then going one more, we have +4, +3, +2. And now going another one, we're doing -1 and -1. And finally, we have the same number. It's constant. So what's the degree? It's not 1, not 2, not 3, not 4, but our degree here should be 5. All right, so that's it for day 1. Let's get started on day 2. So here's the bell ringer for today. Pause the video if you haven't done so already, because I am about to go over the answer. So here we are given a table of a polynomial function p at selected values of x. What is the least possible degree? So yeah, like I said, pause the video now. I'm about to go over the answer. So what we have here is 0, 1, 2, 3, 4, 5. I'm just going to put the table vertically, so it's going to be a little bit easier for us to work with. So -10, -5, -3, 0, 7, 20. And now let's find the first difference. So this should be +5, +2. This should be +3, +7, +13. Going one more deeper, this should be -3, +1, +4, +6. Then we have +4, +3, +2. Now I'm starting to see something. -1, -1. So this should be 2, 3, 4 columns deep. So our fourth difference is the same. So our degree should be 4 of p. All right, so today we're going to be talking about odd and even functions and the types of symmetry that they provide within them. And so it's important to go over our two different types of symmetry that we're going to be talking about today. The first one is reflectional symmetry. This is where you have a line of reflection, and the graph is basically if you flip it over the line. It's kind of like if you're looking at yourself in a reflection, that's what reflectional symmetry is. We also have rotational symmetry. That's where if you have a point of rotation, so for this fidget spinner, let's say we add that black dot and we basically hammer that black dot in with a nail, and you spin that object 120 degrees, that is rotationally symmetric there. And because we take this and we just rotate it 120 degrees around that black dot. All right, so let's start by looking at an example of an even function. And so this even function is going to be symmetric, but how? And so look at this graph and see where is it symmetric and what type of symmetry does it have? And the answer is it is reflectionally symmetric over the y-axis. So basically it has reflectional symmetry. If you reflect the left-hand side over that red line, the y-axis, onto the right-hand side, you're going to get the exact same graph, right? And so what is a property of that? Let's take a look, right? What is f of 2 of this function? Like when we plug in 2, you should get an output of 4. Whoops, that's a really bad line. Let me erase that. When you plug in 2, you should get an output of 4, which equals f of 2. And that means, if it's reflectionally symmetric, that this should be the same as what you get when you plug in f of negative 2. Right? If we find f of negative 2, you plug it in, you also get 4. And this isn't just true at 2 and negative 2. Because it is reflectionally symmetric over the y-axis, it's going to be true at any point, right? 1 and negative 1 are going to have the same y value. So how can we express this kind of in a rule? And the answer is, let's replace 2 with just an arbitrary x. If we know f of 2 is equal to f of negative 2, and this is true for any value, not just 2, but 3, 4, 5, right? Then f of x will be equal to f of negative x, and that is our rule for even functions. Now, if you took a look, why did I choose this function as the example for an even function? And the reason is pretty simple, right? Because of that exponent there. 2 is the most basic even number that we can find. Just kind of like what we did in last class with looking at zeros and multiplicities. I like to take a really basic example and use that to kind of help us learn about maybe more complex examples in the future. Now let's take a look at if this function would be even or not. And the answer should be no. Remember, even functions are only reflectionally symmetric along the along the y-axis. So it would have to be this line of symmetry right here. Unfortunately, this isn't the case, as our line of symmetry is actually going to fall at x equals 1, not x equals 0, which is the y-axis. And so this function would not be even. So big fat no. All right, so now let's take a look at what an odd function is. And so here, for an odd function, this type of symmetry is harder to identify, but it is going to be rotationally symmetric 180 degrees around the origin. All right, so basically what this means is, imagine you take a nail and you stick it in the origin, in the point 0, 0, and you take that graph and you spin it 180 degrees, it should look the exact same. So let's see if we can come up with maybe a rule for this function, because I like coming up with rules, I guess. All right, so if we take a look, let's take a look at the point x equals 2 and x equals -2 again. So if we plug in 2 into this equation, what's our output going to be? It should be 8, right? You plug 2 in, you're going to get 8 as your output. Now, this isn't an even function, right? So we're not going to get 8 when we plug -2 in. Instead, we're going to get, when we plug -2 in, we're going to get -8 as our output. So it's kind of like you have 2, 8, and then you take the negative of both of those, and you get the same thing. So how can we write that, right? Here, f of 2 equals 8, and then f of -2 equals -8. And so what we have here is what we can say is f of -x. So let's say this. Actually, let me start over. So here, let's start with f of -2, right? So we have f of -2, which equals to -8. This is also equal to -8, which I know, duh, right? What does that do? Which is equal to, if we add a negative sign in there, we can add a negative sign out front, -f of 2, which is the same as f of -2 is equal to -f of 2. And then let's replace 2 with the arbitrary value x. F of -x is equal to -f of x. I know this is a little bit of a more weird rule, right? It doesn't come as naturally as even functions do, and that's okay. But I would commit this rule to memory. For odd functions, f of -x is equal to -f of x. All right, and just to show that this function works, because I know some of you still might be confused, let's plug in x equals 2, right? F of -2 equals -f of 2. F of -2 is -8 equals -f of 2, which is 8, and -8 equals -8. All right, so this is our rule for odd functions. Now, this is kind of just a recap of what I said. So even functions is symmetric reflectionally over the y-axis, right there. This is another example of an even function. Odd functions are symmetric around the origin, 180 degrees. And so you stick a nail right there and give it a spin for 180 degrees. It looks the exact same. That's another equation. And so this is true for any even and odd functions. I would know how they look and memorize those rules as well, because those rules will come into play right now. And so you can prove a function is even by substituting in -x and see if you get the same original function, right? So for an even function, the rule, remember, is f of x is equal to f of -x. So if we plug -x in for x right here, and we get the exact same function as the original, then it's an even function. So let's see what this means. We have f of x here, and let's find f of -x, which equals -x to the power of 6 minus 4 -x squared. This is going to be equal to -x to the power of 6. Because it's an even power, it's going to cancel out all those negatives, and we're just going to get x to the 6 minus 4, and then -x squared should just be x squared, which you can almost get rid of the brackets and just rewrite that as this, which is the same original function there. And so that should work, and this function would be even. All right, and now you can prove a function is odd by substituting in -x to see if you get the opposite of the original function. And so what does this mean? Remember, our rule for odd functions is f of -x. So when we substitute it, if we get the original function, but all the signs are flipped, right, -f of x, That is true for any odd function. So let's test this out. Here, you need to do one more step. So first, let's find f of negative x. This is going to be equal to negative 2 negative x cubed plus 5 times negative x. And this, let's see, would be negative 2 times negative x cubed plus 5 times negative x. And so here, this is just those two negatives would cancel, and we would get 2x cubed and then minus 5x. And what we have here is this is our f of negative x. Now what we need to find is we need to find negative f of x. And so you literally just take this function and flip the signs on every coefficient so that negative 2x cubed becomes positive 2x cubed, and that plus 5x becomes minus 5x. Because these two functions are going to be the same, this is going to hold true and will be an odd function. Now we need to show analytically if this function right here is even, odd, or neither. So let's first see if it's even. So remember the rule, f of x equals f of negative x. We know f of x, which is this right here, so there's no need to find it, right? We're given that. Let's find f of negative x, which is 6 negative x4 minus 2 times negative x, which is 6x to the fourth, because that cancels out. And then here the negative is going to be negative 2, and negative x is going to turn into plus 2x. So this is not the same as the original function, so these are different. So then we know this is not even. Now let's see if it's odd. So for an odd function, remember the rule is f of negative x is equal to negative f of x. We know f of negative x because we just found that, right? In the even, that's right there. So we can just kind of copy and paste that, right? No need to do the work again. And now we need to find negative f of x, which is taking this function and flipping the signs. So 6x to the fourth turns into negative 6x to the fourth, and then minus 2x turns into plus 2x. And so these two are different. So this is not odd. So this would fall in the neither category, and this would not be even or odd. So there are functions that are not either or even or odd. I would say that would be the majority of functions. And so just be aware of that as well, that it doesn't have to just be even, or it doesn't have to be odd as well. All right, so example 7. Determine if the following polynomials are even, odd, or neither. And so let's take a look at this first one here. Let's test, so we want to test it using our rules. Let's test to see if it is even first, because that's typically the easier one to test. So here, remember, even f of x equals f of negative x. This should then be 2 negative x to the fourth, if we want to find f of negative x, sorry, or in this case h, but that's okay, it doesn't matter, minus negative x squared plus 5. This becomes 2x to the fourth minus x squared plus 5. So be careful with your negative signs and parentheses. This is the exact same function. So because they are the same, whoops, I forgot the m. Because they are the same, I'll rewrite that. This function is even. So even there, that's good. Let's take a look at this function and let's test to see if it's even first. So for its even, remember f of x equals f of negative x here. Now we already know f of x, or k of x in this case, but let's find k of negative x. Cubed plus 3 times negative x minus 1, which is this turns into negative x cubed minus 3x, and that still stays minus 1. This is f of negative x, which is not the same as the original function, so we know it's not even. Let's see if it's odd now. So this is f of negative x. Let's find f of let's find negative f of x. So that's taking every term in the original equation and just flipping the signs. So negative x cubed minus 3x plus 1. And so these are not the same. They look very similar, but here we have minus 1, here we have plus 1, so this is not the same. So we know this function is not odd either. And so if it's not even and it's not odd, this would be neither for that. So that's A and B done. Those are going to be the harder ones. If we take a look at C, this graph seems that it's obviously not even because it's not reflectionally symmetric along the y-axis, but it looks like it's pretty symmetric rotationally around the origin, right? If we kind of test points, you see negative 1 comma 3, and then you see 1 comma negative 3 as points. This looks like it holds true, so this is going to be an odd function here. And then this graphically, a lot of people want to say so bad that it's an even function, but it's not. That's so wrong. Because remember, this is your line of symmetry, not like x equals 1. So this should be neither. We know it's not even, and we know obviously it's not rotationally symmetric either. So this one should be neither for D. All right, so rules for even and odd coordinates. These are also pretty important. If an even function has the point x comma y in the function, then the point negative x comma y is also in the function. And so let's just take a look at like a numerical example because the notation is a little weird. Pretty much if we have 3 comma 5 and we know the function is even, the other point that has to exist is negative 3 comma 5, right? If you have 3 comma 5 here, if you flip it, reflect it over the y-axis, this point should exist. So that's going to be true. Now for an odd function, it's a little different, right? Because you're spinning it symmetrically, let's say you have 3 comma 5 as a point, then we know negative 3 comma negative 5 is also a point. And so you take the opposite of each coordinate. So in this case, if you have, let's go 4 comma 7, we know for an odd function, if we are given that it's odd, we know negative 4, negative 7 will also exist. All right. All right, so for example 8, we're going to use those XY coordinate rules for even and odd functions to help us answer the next few questions. So certain values of g of x are given in the table. We are given that this function is odd. So typically with these questions, they will say this table or this function is even or it's odd, and then use the rule to like answer or find information about the table. So we know it's odd, which means if we have x comma y, we know that we will have negative x comma negative y on the table. So the first thing that I would do is I would find any coordinate here that's like a full pair, and I would use this to write out the coordinate of the other point that we know for sure. So taking the opposite of both of these xy coordinates, we would have 5 comma negative 10.5. Here we would have 7 comma 22 or negative 22.5. And then here we would have negative 9 comma negative 38.5. And hopefully we can use this to answer our table or fill in our table. So 7, and then we need the y value. This should be negative 22.5. 5, this is going to go with this one right here. And so this is going to be 5 comma negative 10.5. And then this one's going to be paired here, and this should be negative 9. And so that would be example number 8. Example number 9, given that this function is continuous, draw the rest of the graph from negative 5 to 0. So here you want to plot some points. So we know that this is going to just be symmetric along the y-axis. So you go over 1 to the left and up 2. Here then you have 2 units just straight. And then you have a curve. You have a 0 at negative 4. and it just kind of goes down. And so this is 5 units away right here. So we're going to add that curve in. This should be our rough graph to complete that even drawing. And that's just really, kind of finishing the picture a little bit. So number 10, we have the continuous function g of x, and we know this is odd and increasing with selected values shown in the table above. Find the values of a and b. If the average rate of change from -1 to 5 is 2, find the value of c. All right, so let's see. I have this and those two complete points. So I know 5, 9 and 2, 7 should be points. So I see 7 here. So A is probably going to be 2. And then here, 5 is going to be 9. Or B is going to be 9 to fill in those two coordinates. So A equals 2, B equals 9. And then if the rate of change from -1 to 5 is 2, find the value of c. So our coordinates are -1, c, and 5, 9, given from part A. Plug it into the slope formula. So 9 minus c over 5 minus -1, and this slope is equal to 2. This should be 9 minus c over 6 equals 2. 9 minus c equals 12, multiplying both sides by 6. I would subtract 9 from both sides. So -c equals 3, and so c equals -3, and that should be our answer there. All right, so if you have any questions, please come see me in office hours. I will see you guys later.